So now we're working in Chapter 7, which is going to help us to understand how we can use sampling and simulations and sampling distributions to make some inferences about a population from a sample.
So these are the things that are in this section. We're going to be able to distinguish between information about a characteristic of the population, which is called a parameter, as opposed to a statistics, which we calculate from a random sample. We're going to talk about the sampling distribution of a statistic and how we can use that to evaluate the claim about the population itself. So how can we use sampling distributions to help us make inferences about the population itself? We're going to be able to distinguish between population distribution of one sample, and then the sampling distribution of a statistic that relates to that sample. And we're going to talk about unbiased estimators, and we'll learn a lot more about that in class, and then describe the relationship between sample size and variability of a statistic.
So when we're looking to make statistical inference, we have to look at the larger population we're interested in. We're going to collect data from a representative sample, which we've talked about how to collect data accurately with randomization and stratification and all of those different things. It's only when we have that well collected data that we can make inferences about a population. So when we're collecting random samples, we might be looking at different things, and those are the statistics that we're talking about. We've talked about finding the height and the weight and how many times we got 3 heads and all sorts of different things. So the statistics have to do with the sample. And we need to be able to describe the sampling distribution to be able to talk about that population again. So a statistic, by the way, fits in the category of random variables because normally they take numerical values to describe the outcomes of a random sampling process. When you're picking 10 people and asking them a question about something that can be answered with a numerical answer, then it's a random variable, it's a random sampling process, even though we think a lot in terms of maybe rolling dice or picking cards. When you pick 10 out of something, you're also talking about a random variable. Let's look at a couple of examples. Here we have a population distribution. So we're going to be talking about the parameter that is being looked into, which is how many times did you marry? Holy bananas, there's a couple of people that got married 6 times. Holy shoof. Now, if there were of this population of 976, if we took a random sample of 20, and notice n is capital for the population and small for the random sample, then it would be a statistic. How many times did you marry? And here we have a sample population, so this would be a statistic, and maybe this is the sample proportion of people's scores on a AP stats final, and we only have a sample of 20 students, and so we can decide how, based on the quality of our of random sampling, if whether this we can then make inferences about the overall population. So it's really important that we understand the difference between a parameter and statistics. The large population, you're going to be talking about a characteristic, and that's going to be parameters. It's pretty easy. P for parameter, population, S for statistic, sample. We also need to recognize that the symbols that we use are different, whether we're talking about the sample or the population. So the mean of a sample we've been dealing with quite a bit, and that is X bar. And the proportion or percent of a sample is p hat. And then we're looking at the population. The mean is mu. Whoops, my bad. The mean is mu, and the proportion is just a p. So it's important that you recognize what information you're looking at, whether you're looking at a parameter or a statistic. So sampling variability is one of the basic facts that we know that when we take an n of 20 once, it's not really going to give us that much information in terms of the entire population because there's sampling variability. There's just luck. There's chance. So we need to repeat this random sampling lots and lots of times so we get a better sense of how the samples over a lot of
opportunities give us more information about that population. So if we took, let's say we have a population of 10 people, and we have information, a parameter on the number of bags of chips they ate last week. And the first person had 1, and the second person had 2, and the third person had 3, fourth, fifth, and then another person had 1, etc. So 10 people, and this is the distribution, their population distribution of number of chips eaten. Now, if we were to take samples to get a good idea about this population, of course it's super easy just to take a census here, but I'm using this as an example. The sampling distribution would be what would happen if we took 2 of each of this population and all the things that could happen. So all the things that could happen includes, like, you get both of the 1s, and then their average would be 1. But you get a 1 and a 2, and their average would be 1.5 chips, and then the other a 2 and a 1, and et cetera, et cetera, et cetera. And then you would look at the distribution of how that would work out. And it may or may not be a normal distribution, but the sampling distribution of what would happen if we took all the possible samples of the same size from the same population. In practice, obviously, you can tell that's not so hard to do when only 10 people are in the population, but it's pretty hard to do when there's lots and lots of people in the population. So we use sampling to help us understand what's going on, and then we, from there, can use simulation to imitate the process of taking many, 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 many samples. Some vocabulary that's really, really important. Think back to when we picked out the tiles, and some of them were blue and some of them were white. Let's imagine that we have a similar type thing where half of them are blue and half of them are red. And this is a population distribution. The parameter is 50% of them are blue and 50% are red. Then, of course, if you are taking of that 200 chips, you take a random sample of 20. I take 1 and I get 8 reds for every 20. That is my distribution of sample. And then you take 1 and you get 11 out of 20. So that's 55%. And then someone else takes 1. These are distributions of sample data. But then when we put everyone's data together after many, many simulations, this is the distribution of this sampling. So we need to understand the parameter is what we're looking for in this case, the proportion that are red, and then each of us, as we're doing these simulations, would get our individual sample data, and then it's put together for a sampling distribution. And then the sampling distribution is what's going to allow us to make decisions about if something occurs, if it's strange or so rare that we can consider it statistically significant. So the last thing we're going to talk about here is whether an estimator or a statistic is a good estimator of the parameter or if it's not. And so biased estimators are going to be ones that are off target. They just don't hit it. And unbiased estimators are going to hit that target. It seems pretty straightforward. So if we collected many samples of that size 20 and put a lot of them together and we got our sample distribution, how well does the sample proportion estimate the true proportion of red chips? Well, if we balanced out the 0.8 and the 0.2 and all the 0.7s with the 0.3s, it would all work out to be exactly 0.5. And so this is considered an unbiased estimator. If the mean of its sampling distribution is equal to the true value of the parameter being estimated, then it's unbiased. If it's off target consistently, then we consider it a biased estimate. So we want to start when we're looking for an understanding of a population. We obviously want to start with an unbiased estimator, but that's not enough. It does allow us to tend not to overestimate or underestimate, but that doesn't guarantee that the value will be close if we end up with sampling variability that just skews us in a certain direction. So we got to make sure that variability is as low as possible, and that occurs when we increase the number of trials, increase the number of, and we're going to do quite a few simulations to understand why this is so. But the larger the sample size, probably the closer you're going to get to the parameter value, assuming that it's an unbiased estimate. So how can we decrease variability? increase the sample size. That's a pretty common and clear understanding of the ways we can increase our ability to make statements that are accurate about the parameter of interest. So the statistic is a good estimator when we know it's unbiased and we have lots and lots of trials to base it on. Interestingly enough, though, the size of the population doesn't really affect the variability of the statistic. It's all about the repetition of the sampling and the large number of trials. So there is a statistic that you need to be aware of. We know that larger samples give smaller spreads, but the spread of the sampling distribution doesn't depend much on the size of the population as long as the following is met. So if you can take the sample size and it's less than or equal to the population, then you're fine. Then the size of the population doesn't really affect it. So if we have 100 people, we don't really want our n to be any bigger than 10. For those of us that like a visual example, so we need our statistics to give us a good idea of the parameter of interest. And there's two things that can keep that that inference from being accurate, and one is bias. And here's a visual of bias. Bias, this is high bias in both cases. High bias means here's our target. We're not hitting it consistently. In this case, it's consistently off target, and this one's it's inconsistently off target, but it's still off target. So this is high bias. Here, these are closer to the target, but this one's all scattered all over the place, close to the target, and then this one is right on. So this right here would show visually this would show a statistic that is unbiased and that there's enough samples that we're going to get low variability as well. So I actually did the entire section, and that was not my intention. We'll see if this is gonna make it or it's too long.